October 5th, 2025, the Very Large Telescope releases data that shakes the scientific world. 3I-ATLAS is producing nickel extreme amounts at temperatures of -150 degrees. This should be physically impossible. And nobody can explain why it's happening anyway. Stay with me, because this data changes everything. Dr. Denny Hutsmakers sits in his office in Liège, Belgium. In front of him, the latest spectroscopic data from the UVS instrument at the Very Large Telescope. He's analyzing the light from 3I-ATLAS, the third interstellar visitor ever detected passing through our solar system. What he sees doesn't make sense. The nickel emission lines are extremely strong, far stronger than any other comet he's ever observed. He checks the calibration once, twice, 3 times. The data is correct. He compares it with the database of known comets. Dozens of objects, decades of observations, nothing comes even close to what 3I-ATLAS is producing. And then he makes the calculation that changes everything. The nickel to iron ratio. In normal comets, iron is more abundant than nickel. This is a fundamental rule of stellar nucleosynthesis. Iron is produced in larger quantities in stars. In 3I-ATLAS, the ratio is reversed. More nickel than iron. He leans back, stares at the numbers, and writes the sentence that will circle the globe in the coming days. The presence of nickel and iron atoms in the coma is extremely puzzling. The scientific community reacts immediately. Within 48 hours, the data is verified by teams worldwide. Harvard, MIT, Caltech, ESO, NASA. Everyone comes to the same conclusion. The data is real. 3I-ATLAS is producing nickel at temperatures that are far too low, and nobody knows why. But that's just the beginning. The data shows something else, something many have overlooked. Stay tuned. Nickel is a refractory metal. That means it requires extremely high temperatures to vaporize. Over 1,000 degrees Celsius, 3I-ATLAS is currently about 400 million kilometers from the sun. Surface temperature is -150 degrees or colder. There is no known natural way for nickel to sublimate under these conditions. But it's happening. Massively. Anomaly 1, the nickel production. Dr. Hutsmakers and his team create a graph. On the x-axis, the total production rate of nickel and iron combined. On the y-axis, the ratio of nickel to iron. Then they plot all known comets. Dozens of data points, different colors, diamonds, squares, circles, all clustering in a tight region at the bottom left. Normal, predictable, understood. And then they plot 3I-ATLAS. Red squares. Far up to the right, completely isolated. Not even close to the other comets. It's like creating a graph of mammals and suddenly a dinosaur appears. It doesn't fit any category. This isn't just a statistical deviation. This is a fundamental difference. Anomaly 2, the C2 depletion. Comets glow green because of diatomic carbon. C2 molecules, they break apart under solar radiation and produce the characteristic swan band emission. The more active a comet, the more C2 point. 3I-ATLAS glows green. But the spectroscopic measurements show the C2 concentration is extremely low. This is called C2 depletion, carbon deficiency. Hutsmakers writes in his report, 3I-ATLAS is a C2 depleted comet exhibiting extreme properties in the early phases of its activity. The green glow is there, but the carbon is missing. It's like a car that drives but has no engine. Something else is producing this color, and we don't know what. Anomaly 3, the Borisov comparison. In 2019, 2I Borisov passed through our solar system, the second interstellar visitor. Scientists analyzed it with the same instruments, same spectrographs, same methods. Borisov showed nickel and iron in its coma, but the ratio, completely normal. Just like comets from our own solar system. Textbook, why is one interstellar comet normal and the other extremely abnormal? Both come from outside our solar system. Both are billions of years old. Both were ejected from their home systems, but one follows the rules, the other breaks them. What's the difference? The scientific community is divided. Some say natural, others aren't so sure. And then there's Avi Loeb, stay tuned. Avi Loeb sits in his office at Harvard University, former chair of the astronomy department, head of the Galileo project. A man who's not afraid to ask uncomfortable questions. He reads the report from the Very Large Telescope and writes an article that goes viral within hours. The title, New Data on the Extreme Nickel Production of 3I-ATLAS. He starts with the facts, the measurements, the graphs, all scientific, all documented, and then comes the sentence everyone's been waiting for. We should not judge the nature of 3I-ATLAS by the chemicals evaporated from its surface for the same reason that we should not judge a book by its cover. What does he mean by that? Loeb argues, what we're seeing is only the surface, the outermost layer. Maybe that says nothing about the interior. Maybe there's something completely different inside. He continues, nickel on Earth is primarily found in industrial alloys. High nickel steel, designed for extreme strength, corrosion resistance, high temperatures, critical for aerospace technology. Oumuamua 2017 showed non-gravitational acceleration without visible outgassing, behavior that to this day hasn't been fully explained. 3I-ATLAS shows extreme nickel production at impossible temperatures, behavior that contradicts the laws of physics. Loeb asks the question directly, could 3I-ATLAS be artificial? The reaction is immediate. Half the scientific community says too speculative, too sensationalist. The other half says we shouldn't rule it out. Loeb adds, if 3I-ATLAS maneuvers toward Earth when it reappears on the other side of the sun, the financial markets may crash. A dark joke? Or a serious consideration? He continues, for now, I eagerly await with optimism that the new data from the Mars orbiters will alleviate these concerns.
The Mars orbiters!
On October 3rd, ExoMars Trace Gas Orbiter and Mars Express flew within just 30 million kilometers of 3I-ATLAS. They took images, they captured spectra. The data is being analyzed right now. The high-rise camera on Mars Reconnaissance Orbiter has a spatial resolution of 30 kilometers per pixel. That's 20 times better than Hubble at this distance. If 3I-ATLAS has structure, we'll see it. If it's just a lump of ice, we'll know. The results are coming in the next few weeks. But there's another theory. The theory nobody says out loud, but everyone is thinking, what if 3I-ATLAS comes from a star system that's completely different from ours?
What if the chemistry there is fundamentally different?
What if nickel is the most common component of rock there? Then what we're seeing would be completely natural. Just natural under conditions we've never seen. That's the elegant solution, the scientifically conservative answer. But it doesn't explain the low temperatures. It doesn't explain why nickel is sublimating when it should be physically impossible. It doesn't explain why Borisov was normal and Atlas is extreme. And that's exactly why the debate remains open. On October 29th, 3I-ATLAS reaches perihelion, 0.36 astronomical units from the sun. Speed, 68 kilometers per second. This is the moment of truth. If it's a natural comet, the extreme solar radiation will either cause it to explode or break into fragments. If it's something else, then we'll know in 24 days. But there's another dimension nobody mentions, a connection that goes back 10,000 years. Stay tuned. Let me tell you something that's not in any scientific paper. Dr. James Davenport from the University of Washington analyzed the galactic trajectory of 3I-ATLAS, where it came from, how long it's been traveling. His conclusion, the trajectory aligns with the thick disk of the Milky Way, a region populated by older stars. Older stars, stars that formed when our galaxy was young. 10 billion years ago, maybe more. That means 3I-ATLAS could be carrying chemistry from an era long gone. From a time when the Milky Way looked completely different, when the chemical composition was different, when the ratios of elements were different. Maybe what we're seeing isn't abnormal. Maybe it's just old, so old that our models no longer apply. But here's where it gets really interesting. Nickel anomalies have been found on Earth before. In the Cretaceous-Paleogene boundary, the layer that marks the extinction of the dinosaurs, there, they found a thin layer with high nickel concentrations, proof of a massive asteroid impact 66 million years ago. Nickel is rare on Earth, but common in asteroids, especially in metallic asteroids, remnants of protoplanets that were destroyed in the early phase of the solar system. What if 3I-ATLAS isn't a comet, but a fragment of a destroyed planet? A metallic core coated with ice. That would explain the nickel. That would explain the extreme production. That would explain why it behaves differently than normal comets. This theory has been proposed, quietly, carefully, but it has a problem. Metallic cores don't sublimate at -150 degrees. And even if they did, they wouldn't form a coma. No glowing gas envelope. no green coloration. So we're back at the beginning, an object that behaves like a comet but has the chemistry of a metallic asteroid. A contradiction that cannot be resolved, not with our current physics. Dr. Ariel Graycowski from the SETI Institute coordinates the observation campaign with the Unistellar Network. Hundreds of small telescopes operated by citizen scientists worldwide. People who simply look at the sky and ask, what's out there? They stack images, they combine data. Together, they achieve what a single telescope couldn't. Graycowski says, early brightness measurements reveal a steep increase. This is consistent with dynamic new comets making their first close approach to a star for the first time in billions of years. Whatever was frozen in 3I-ATLAS is awakening now, and what it's showing us doesn't fit in any box. In the coming weeks, 3I-ATLAS will disappear behind the sun. Superior conjunction will be blind, but in November, it returns. Transformed by the heat of the perihelion passage, maybe fragmented, maybe brighter, maybe darker, ESA's JUICE mission will observe it, on its way to Jupiter. With cameras, spectrometers, particle sensors, the data will show what the solar passage did to the object. Whether it survived, whether it changed, whether it's still producing nickel, and someday, maybe in a few months, maybe in a few years, someone will find the answer. An answer that will either revolutionize our models of comet physics or our understanding of what's possible in the universe. Until then, the question remains open. What is 3I-ATLAS? A comet from an alien world with impossible chemistry? A fragment of a destroyed planet? Or something we can't even imagine yet? The data speaks, but physics is silent. And the nickel? The nickel remains a mystery. The truth is out there. It's 400 million kilometers away. It's moving at 68 kilometers per second. And in 24 days, it reaches the sun. What happens then? Nobody knows. Not yet.